Okay, we're going to continue on here. We're kind of finishing one chapter, previewed another, I suppose. So we're still kind of finishing up chapter 11 a little bit here, what's left. Last time we talked about some different organic groups. So as we've been talking about, remember that there are functional groups, which basically are the part of those organic molecules that makes them a specific type of organic molecules. We've had our alkanes, which really sort of it's carbon-carbon single bonds happening. We have our alkenes, which is our carbon-carbon double bond. We have our alkynes, which is our carbon-carbon triple bond. We previewed, and we'll talk more about it today as well, alcohols, which have a functional group of OH. And this functional group is really sort of the part of the molecule that pretty much everything sort of happens. If there's any type of reaction that's going to happen, it's going to really sort of happen at those functional groups. The way we name pretty much everything in organic chemistry is pretty much based off of those first 10 alkanes, as we talked about. And we just do some slight adjustments depending on really what type of organic compound we have. Alkanes will end in ANE. Alkenes will typically end in ENE, just like the group name there. Alkynes will end in YNE, and alcohols will end in OL. So no matter what you're sort of naming, as we've been talking about, really the first thing that you really want to look at is to find the longest continuous carbon chain. And remember that that longest continuous carbon chain doesn't necessarily have to be the straightest. It can kind of go straight up and over, but it does usually has to contain the functional group. So again, if you have a double bond sort of happening in there, you can't sort of count around the double bond. It's got to be part of the longest carbon chain. Same thing with triple bond and so forth. Once you have that, that will really give you sort of the base of the name. You will change the ending depending on obviously what functional group you're dealing with. A couple additional things that are different as well. When we do have a double bond, a triple bond, or even the OH group here with our alcohols, if there is sort of more than one option as to where those functional groups can end up on that longest carbon chain, you do also need to give the number of where those are located. And that's usually, I would say, in most things, pushing about 4 or more carbons is sort of where that starts, or in some cases even 3 carbons. In the case of an alcohol, you do have to give the number of where those guys are located. Now, when we number the longest carbon chain, it's always the functional group that takes the priority in terms of numbering, and we want to number whichever way gives the functional group the smaller number. So basically, we want to number that long chain that gives the functional group the smallest number. Now, the exception to that would be alkanes, since they're all carbon-carbon single bonded. We do want to number alkanes in a way that gives the groups the smallest number. But when we have double bonds, triple bonds, or OH groups involved, those take the precedent in terms of which way you should number. And as we talked about last time, once you sort of lock in that numbering, any other group that's not part of the longest carbon chain is numbered accordingly. So you don't renumber going the other way or something like that. So sort of once you lock in whichever way that you want to number that longest carbon chain, that pretty much locks in the numbers for anything else that may be attached in that particular molecule. Then at the end here, kind of we do our groups in alphabetical order. Once again, regardless of a prefix like di or tri or tetra, we do again our between a number and a letter, the dash. And again, if we have 2 numbers, we do commas. And I think we did a few examples there the other day. where again, if you do have the same group on the same carbon, you do need to give the same number twice. Yeah, so that's how we get things like 3,3 or something like that. So you do have to give that number twice when you do that. Now, we also talked about cis and trans isomers. And basically, cis is the same side and trans is the opposite side. And what we're talking about is the double bond here. So again, that would be more of a cis situation with these guys here being on the same side. And we could also have a trans sort of situation where these guys would be on opposite sides of the double bond. This occurs because when we lock in that double bond, we actually lose the ability to just kind of freely rotate around that single bond like we have with the carbon-carbon single bond. So that really will then lock everybody into place, either kind of above the double bond, below the double bond, and that's what we're looking for. Remember that there are two things that you want to look at to determine whether or not you can even have a cis or trans isomer. You got to make sure that you have two different groups on each carbon in the double bond. And you also need a group that's similar on opposite sides of the double bond or opposite carbons. And then you could have a cis or trans. Again, if you came across a double bonded type situation where when you look at one of the carbons, let's do H. One of the carbons here has two of the same groups. That means you cannot have cis or trans isomers occurring. So they do have to be different groups on different carbons, and then you should have a similar group between the two. We also name some of those where we just add cis or trans to the beginning of the name. The other important thing is, again, you want to get still the longest carbon chain. I think maybe some of you might have had just the two for everyone on that example that we did. So you guys still start from beginning to end. It's not just the two carbons there that are in the middle. We also talked about the idea that if you do need to draw something in the cis or trans sort of drawing to show cis or trans, a lot of times it's easier just to draw it just straight without the cis or trans. And then once you do, you can just isolate your double bond and figure out your four groups that are there. And then you can redraw it kind of with the cis or the trans, depending on what you need. Lastly, I think we sort of finished up there with some reactions. We talked about addition reactions. And those were with alkenes, which is our double bonds. And addition reactions, as we talked about, means that we're going to add basically two things to the double bond. So always in these addition reactions, basically for alkenes, your double bond becomes a single bond. And that then leaves room for whatever may be coming in. And they can come in on opposite carbons. They never come into the same carbons. And again, this would be something like, for example, we added hydrogen, which is a symmetrical addition, sometimes referred to as a symmetrical addition because you're adding two of the same things, which means you can't really choose wrong. When you do this, you should not overthink it, other than that double bond should become a single bond. And that is really the only place in an alkene that's going to change in these reactions. Everything else is going to be identical. So as we talked about, you pretty much have your structure that you need in the actual left-hand side of the arrow. You just want to draw it exactly the same, turning that double bond into a single bond. And at that point, once you do that, you will now have room for those two hydrogens to come in, once again, one on each side. This takes us from an alkene to an alkane. This is what is known as a hydrogenation reaction because we added hydrogen, basically. And just like when we make a double bond or a triple bond, we lose two hydrogens. when we put the two hydrogens back, we get rid of the double bond or the triple bond that may be there, depending on how many hydrogens we put back. We also could do a unsymmetrical sort of addition, and in an unsymmetrical addition, you're adding something like hydrogen and something else. For example, like water, like HBr, HCl, hydrogen, and something else. And in these unsymmetrical additions, nothing much is different other than we still have our carbon-carbon double bond that will become a single bond. Everything else will look, once again, exactly the same. And in this case, that now will make room for our hydrogen to come in and our OH in this particular case. And in this case, this is what is known as a hydration reaction. We go from an alkene to an alcohol. So this is one way that you can make an alcohol, is by throwing water at an alkene, and it will do this. Now, in this case, it's unsymmetrical because you're adding two different things to that double bond. So in some cases, it does matter where the hydrogen ends up or doesn't end up. And that's a situation where when you look at your carbon-carbon double bond, there is a difference in the number of hydrogens that are there to start with. So if I read you this here, like maybe this. And now I added my water or my HCl or HBr. When we do this, we are still going to pretty much draw exactly that same structure that we started with. The only difference here is we're just going to make that into a single bond. Once again, you shouldn't get fancy with it. Yeah, nothing much changes other than that double bond becomes a single bond. I think we might have talked about it last time. You know, no weird rings start forming or any of those kind of weird things. So all you really have to do is just copy what is there and just do your change there to our double bond in this case to make it a single bond. Now, because there's actually a difference in the number of hydrogens attached to the carbons in the double bond, there is a rule known as Markovnikov's rule there, which says the hydrogen will end up on the carbon that started with the most hydrogens. So this guy has two hydrogens, and that carbon has one hydrogen that's directly attached to it. Again, these hydrogens are not directly attached to that carbon in the double bond. They're attached to the other carbon that's sitting out there. So that means that really the proper major product would be putting the hydrogen over here on the right. And in this case, our OH group would end up on the other carbon in this case. So that's the one thing you have to kind of watch out for with addition reactions of alkenes is if at that carbon-carbon double bond, you got some differences in the hydrogen. When you add the hydrogen, when you add water, or again, if you added something like HCl, HBr, that hydrogen should always end up at the carbon that had the most hydrogens to begin with. Any questions on that there? We also talked about a few other reactions towards the end there that we kind of jumped ahead, but since we talked about it, let's just review those and we'll see them again here in a second. But we did talk about some alcohol reactions that happen. And alcohol reactions can have a really a redox sort of reaction, which is an oxidation reaction, which is sometimes abbreviated in organic chemistry with this little O in brackets. It means you're going to put it through oxidation. Oxidation in the case of organic chemistry usually means one of two things. It does mean loss of electrons, but usually in organic chemistry, we're not so interested in electrons. But it also will mean that you gained gained oxygen from reactants to products, or you lost hydrogen from reactants to products. Reduction, as we talked about, I think in an earlier chapter, they always sort of happen together. Reduction, oxidation always occur at the same time. Reduction means it gaining electrons, but also means that you lost oxygen as you go from reactant side to product side, or you gained hydrogen. as you went from reactants to products. So when we look at an alcohol, such as this one here, do this. This alcohol is a primary alcohol because when we look at the carbon that has the OH group, it is directly attached to one other carbon, which makes it a primary alcohol. And when we oxidize, again, a primary alcohol, the definition of oxidation that's going to happen with these alcohols is the loss of hydrogen. And it's going to be really this definition here. And that's actually H2. And when you have an alcohol and it goes through oxidation, it's always going to take the hydrogens from the same spot. You should always pop a hydrogen off there from the oxygen in the OH group. And you should also take a hydrogen there from the carbon that is attached to the OH group. So those are always where the two hydrogens come from. Just like we saw with our alkene, right? When we put the hydrogens on, they went on to separate carbons. When we take the hydrogens off here, we take them from separate carbons as well. So it kind of works the same way. When we do that, that's really what's going to give us our loss of H2, which is why it's be called an oxidation reaction. And once again, you shouldn't overcomplicate the drawing here. You should pretty much draw exactly what's there without the two hydrogens, basically. So that's all you need to do is just copy exactly what was there, exactly the way it looks. Again, without the two hydrogens in this particular case, and it'd probably be good if I threw an extra hydrogen on there for good measure. So I had the right number of hydrogens to start with. And now we copied it exactly the same way. And what always happens in this case is after we lose the hydrogen, we basically put on a bond between carbon and oxygen. So carbon and oxygen is always where those bonds get put on. So we'll put on our double bond right there. And so in the case of the oxidation of an alcohol, we lose H2, then we double bond the carbon oxygen. So that's pretty much always the deal. This all you have to remember, take off the two hydrogens in the right location, lay up a double bond between the carbon and the oxygen, copy everything else exactly the same. This makes, again, a different sort of organic molecule, which is known as an aldehyde. And an aldehyde has the functional group of carbon oxygen double bond and that hydrogen that is there. Now, if we take a secondary alcohol, which I'll try to draw a little bit better here. I'll do this guy here and this guy here. Once again, this carbon is attached to the OH group, has one carbon and two carbons attached directly to it, and that is a secondary alcohol. So when it goes through its oxidation, just like above, all you have to remember is take away the hydrogens. So always one hydrogen from the oxygen and one hydrogen from that carbon that's attached to the OH group. That again is going to give us our loss of hydrogen, which is again the oxidation part of this. And at this point, I'm just going to copy exactly what I got going on there. So we got CH3, we got carbon, we have an oxygen, and I have a CH3 over here. And the other thing I'm going to do at the end is put a double bond there between the carbon and the oxygen. And when I do that, put it right about there. That will give me another organic group, which is known as a ketone. And a ketone has the functional group of 3 carbons in a row. And on that middle carbon is where the carbon-oxygen double bond is. And that would be that guy right there. So the oxidation of a secondary alcohol, as we talked about there, will yield you a ketone. It's the exact same reaction from above. And again, as you can see, nothing funny happens with the molecule. Only at the functional group is where it will change. A tertiary alcohol something like this. And this is a tertiary alcohol because, again, our carbon here attached to 1, 2, and 3 carbons. When it goes through oxidation, we will get no reaction occurring. And we get no reaction because we do have 1 hydrogen here, but we are missing the crucial sort of second hydrogen that is necessary there on the carbon. So because we do not have that second hydrogen here in the center to be lost so we can lose H2, this guy will not go through an oxidation reaction. Any questions on that there? What we're looking at here in all these cases are the oxidation reaction. If you wanted to undo it, the reaction would go in this direction, and this would be the reduction reaction for all these. And the reduction reaction would be adding hydrogen back in, and going the backwards would be the reduction reaction. So oxidation makes the aldehyde for the primary, ketone for the secondary. If you actually want to reduce it back down to the alcohols, you just add the hydrogen back, and it would go back at the double bond spot, just like kind of with the alkane. Any questions on any of those sort of reactions and stuff that we talked about last time there? Okay, then let's finish up the last few slides or so on this handout here from 11. So we just talked about it again. It's sometimes classified that addition reaction when you add hydrogen, known as a hydrogenation reaction, and that's essentially getting rid of double bonds and making them single bonds. So that's going to go from an alkene to an alkyne, and again, in this case, it's a symmetrical addition, which means 1 hydrogen goes there, 1 goes there. We get rid of our double bond to make room for those guys to come in. Also up here, these are catalysts. And catalysts are sometimes written above the arrow. Catalysts are substances that are not reactants. They're not products. They're just there to basically make the reaction occur faster. So sometimes you see some of those things written up there on the arrow. That's essentially what those are. They really have no sort of effect on the drawings or anything like that that we would be doing, but they are sometimes key to allowing this reaction to basically occur. So this again is a symmetrical reaction, which means you can't really ideally mess it up because you're adding the same element to each carbon, so it doesn't really matter where you put it. Similar symmetrical additions, if you add something like Br2, 2 Brs come in, Cl2, 2 Cls come in, 1 to each of the carbons. So again, it doesn't really matter in that particular case. As I might have mentioned, this is sort of the process that's used to turn oils into things like margarine and stuff like that, because as you get rid of those double bonds, everything in terms of fats come together nicely, or nicer, and it becomes more from a liquid to a solid phase. So that's sort of how they sort of turn things into like margarine from like olive oil and oils and things like that, is they get rid of a bunch of double bonds, and then it becomes more of a solid at room temperature. So why don't you try this? Write the reactor for the hydrogenation of 1-butene. Okay, let's take a look. So obviously to do this, we should start with the correct structure here. So I see ENE, which tells me it should be a double bond, right? So that tells me I got a carbon double bond. I see butene, which tells me is based off of butane, which should be 4 carbons, I believe. And 1-butene would mean that the double bond should be at carbon number 1 there, right? Now we can fill in some hydrogens here. So we got 3 on this guy. This guy's going to be 2. For the double bond area, I'm going to actually draw out the hydrogens so we can see it. So this guy would have 1 hydrogen here, and this guy should have a couple of hydrogens there, right? So at this point, this is our sort of correct starting structure of 1-butene. Any questions on that there? Now we're going to do a hydrogenation, which means we're going to add hydrogen, basically. So we're going to add H2, which is basically 2 hydrogens together. And again here, the only part I really should concern myself with is where that functional group is at, and that is right here at the carbon-carbon double bond. And I know that this is an addition reaction with an alkene, which means I know that all I have to do is copy what's there and turn my double bond into a single bond. So that's all I'm going to do is pretty much just copy exactly what's there. So we'll have our hydrogen, our carbon, our hydrogen, single bonding our carbon there, our hydrogen, and we'll kind of keep it like this. And now that I did that, the purpose of that is we now have room for each of these hydrogens to come in. And again, they do come into one carbon at a time. They do not come into the same carbon. So that means that this guy here will make a different color, gets a hydrogen, and this guy here should also get a hydrogen as well. Any questions on that there? So again, we go from an alkene to an alkane, and sometimes that's good to also know for reference point that when you go to draw these things, you kind of know what you should be drawing there at the end. And if you draw something different, hopefully you'll be able to catch yourself. Any questions on that one there? So as I mentioned earlier, this is a process that is used with fatty acids to really sort of make the melting point higher, and it does turn oils more into a solid version, hence our margarine over here, or shortening. And that's because when we get rid of these double bonds, as we'll talk about when we get to that chapter, it allows this part of the molecules, when you got a bunch of them together, to sit really nicely with each other. So they actually will sit right on top of each other and really sort of compact and interact well with each other, and they'll become more solid. When you have a double bond, as we'll talk about, what happens is it actually makes kinks in those chains. So that chain back here cannot sit nicely. So you got one kind of going that way, you got some coming that way. So they're not going to sit really nicely with one another. And that's really why those guys with double bonds, as we'll talk about when we get to that chapter, is mainly like oils and stuff like that, more of like a liquid at that point, because they have much lower melting point, because they can't really associate with each other, because the double bonds kind of swap the back part of the plane in these weird sort of orientations. They sometimes refer to as having kinks in the chain. So it kind of kinks up and down, so they can't really interact really nicely. You get rid of those double bonds. When you get a bunch of these guys together, they sit really nicely with each other. And that allows those carbons to interact well with one another through dispersion forces. All right, a couple more here. Draw the outcome here of these reactions. Let's change this. Okay, so let's take a look. And once again, as bad as this may sound, you should not overthink these things. Yes, so you just keep it very, very simple. Once again, I see a double bond, so pretty much I know that's pretty much where everything's going to occur. So, and because this is an addition reaction, I also know all I have to do is just turn that into a single bond. And that's really should be your first step of what you should do, is pretty much just copy what's there. So I should still have a CH3. I should still have a C. I'm just going to draw the hydrogens out just to make it a little clearer, hopefully. That double bond now is going to become a single bond, and I will have a carbon at the other end of it. And that guy also has a hydrogen to begin with. And we have another CH3 at the end there. So again, nothing fancy happens other than we just need to make some room for these guys coming in. At this point, it is a symmetrical addition of two hydrogens, which means we just then will put a hydrogen on either end there, or either carbon. And obviously, if you did it all condensed, you would end up with CH3, CH2, CH2, CH3. But either way is fine in this case. Any questions on that one? Yeah. All right, so same deal here. I see a double bond. So frankly, that is still where everything's going to happen in this case. This does not open up and become anything else. It still stays exactly the same. So all I'm going to do is recopy that exactly the same and just get rid of the double bond. So that makes it pretty straightforward. If I draw it better, there we go. And now same thing is going to happen here. Is basically Cl2, and they're going to go where those double bond originally was, because now we technically have room for it. And we're going to put a Cl and like a Cl, and then we're going to put nothing else, perhaps, yes. By the way, there was originally, when we looked at it here, there was originally obviously a hydrogen at each of those. They're still there, by the way. It's still here. Again, this is more line structure, so usually not drawn, but it is still present at that point. Any questions on those there? All right, so we also talked obviously about our hydration reaction where we add water. And again, you can think of water, as we've been talking about, as H and OH. And same thing, you just got to watch that rule there. I spelled it there, Markovnikov rule, that guy's rule, which basically again says if there happens to be a difference in the number of hydrogens to begin with in the carbon-carbon double bond, that hydrogen that's coming in should end up at the one that had the most hydrogens to start with. And again, in this case, we're talking about addition of like water as HOH. We're also talking about addition of things like HBr. That would be H and Br coming in. Our HCl, which would be H and Cl coming in. So those are all, again, those unsymmetrical additions. If there really is no difference in the number of hydrogens, then it really doesn't matter where you put either one. It will end up with the same sort of guy at the end there. This, again, is how we make an alcohol. We make an alcohol from basically hydrating an alkene, and we will get that OH group that happens there. You, again, will sometimes see H2SO4 written in, and that's a catalyst, so it has nothing really to do with drawing anything or interacting. Or you may just see generically, like you see here, up on top of the arrow, H+, and that usually just means that an acid is being used as a catalyst. So that's just a generic sort of formula for an acid as a catalyst. So the same rules apply. We're just going to double bond to a single bond. And again, OH to one carbon, H to the. Okay, so looking at this, if it helps you, and you may want to redraw this and maybe just kind of draw out the hydrogens around the double bond. So if we do that, I can leave the other guys kind of alone if you want. I'm just going to draw out my hydrogens there around my double bond. Again, I know that this is pretty much where everything should occur. So we really just want to focus in on our double bond, and we really could just start drawing our product at this point, because again, we should know that it should become a single bond. So we pretty much got 99% of it done already. So we could just redraw it here. And again, the difference is as we come across here, we're going to turn that into a single bond, and that's going to give us room to add what we are adding in this case, which is our hydrogen and our OH from water. And at this point, we do want to always kind of look at the double bonded carbons and sort of look at the hydrogens we got going on, which is why sometimes it might be easier to draw it out so you can kind of see it a little bit easier. And we do see that the guy on the right there has 2 hydrogens. The one on the left there has 1 hydrogen. That means it does make a difference, right, where I put my hydrogen. And the hydrogen should end up on the carbon on the left or the one on the right. Hydrogen should end up on the right. It has more hydrogens to begin with. So that is where we should add our hydrogen, which means by default there, that is where we're going to add our OH group there to make our alcohol in this case. And that would be what alcohol? That has 4 carbons, which means it's based off of butane. And since it's an alcohol, it is now butanol, right? And the OH group is located at carbon number 2, right? 1 and 2 coming that way. So that would be 2-butanol. Primary, secondary, tertiary alcohol. It is a secondary alcohol, right? That carbon where the OH group is attached has 2 carbons directly attached to it. So we would be looking at this carbon that has 1 and 2 attached to it, which would make it a secondary alcohol in this case. Any questions on addition reactions? All right, so to finish up this chapter here, we're going to talk about another sort of organic group, if you will. And these are benzene-based groups, and these are aromatic compounds are sometimes referred to. And the basis of the aromatic compound is this 6-carbon ring group that basically has 3 double bonds in it. So it looks something like this, where it has those 3 double bonds. You could draw a resonance structure where the double bonds move to the other side. And very commonly, as we might have mentioned the other day, sometimes you'll even just kind of see a circle drawn in the middle. And that's because there's resonance structures and those double bond electrons are just moving around. So at any given point, they could be like the guy on the left or the guy on the right and so forth. That is a 6-carbon ring that has a hydrogen at each of the carbons. So there's a hydrogen hanging out at each of these carbons as well. This, once again, should not be confused with this guy with no double bonds, which is cyclohexane, nor should it be confused with this guy with like 1 double bond, which is cyclohexene. You need 3 double bonds to become benzene. Yeah, so sometimes people get them confused. They just kind of see the ring and just jump to, oh, it's like benzene or something like that, because it kind of looks like that. So again, there are things that look similar to it, but in order for it to be benzene or sort of an aromatic compound, it does have to have those 3 sort of double bonds, or sometimes in books like the one we use here, they probably may just lay up the circle in there to imply that it has those 3 double bonds. Benzene is displayed like we see here on the bottom in many different ways, but it is a little bit different than those other guys that we just talked about. Now, a couple of things that does occur with benzene is there's some historical sort of names that people kind of still use today when you have certain groups attached to a benzene. And those names are some of them down here that you should be familiar with, because again, they will sort of pop up every so often. So if you have a benzene ring with a methyl group attached, it is what is known as toluene. So if you see toluene, it is a fancy word for a methyl group on a benzene. If you have just one group attached to a benzene ring, you just name the group and you put benzene at the end of it. So another name for that guy is methyl benzene. So toluene and methyl, because that's the group attached, and benzene. So if you have just one group attached to the benzene ring and it's maybe not a historical sort of name, or even if it is, you can just name the group and put benzene at the end of it. This is aniline, which is a benzene ring with an NH2 group on it. This is phenol, which is an alcohol that has an OH group on a benzene ring. So those 3 you should be familiar with, because still today people still sort of use those names with benzene involved. So if you kind of see those names pop up, it will be, one of these guys is part of it or the main part of it. Any questions on that there? Now, again, if we have some things substituted on it, as I mentioned before, if it's mono-substituted, which means we have just one group attached, you simply just name the group and put benzene at the end of it. So this is our benzene ring here, and we have a chloral group attached. So that is known as chloral benzene. Because there's only one group attached to that benzene ring, you don't need to give the number of where that group is attached, because it's assumed to always be carbon number 1. Yeah, so that guy will always be carbon number 1. So you don't necessarily have to you shouldn't give the number with it. Now, when you get multiple groups there, you do have to start giving some numbering. So in this case, on the right there, we have still benzene as the base of our name. And we have two chloral groups, which is where the dichlorobenzene comes from. And we do need to give the numbering here. The nice thing about the benzene ring is it's 3 double bonds, which means, as we talked about when we did cycloalkenes, when you number, you have to go through a double bond. In this case, because there's 3 of them, you could go either way, and you will always go through a double bond no matter which way you go. So you could just go whichever way gives you the smaller number. And in this case, going from clockwise here will give us a 1 and a 2 for those locations, and that is known as 1,2-dichloral benzene. If we have it at the 1 and 3 location, as you can see there, that is 1,3-dichlorobenzene, and the 1 and 4 location is 1,4-dichlorobenzene. When you have a benzene ring and you got a couple of things attached like this, there's also an alternative way that they are named, where we don't use numbers, but we use letters and names. This 1 and 2 positioning is what is known as the ortho positioning, or the O. And instead of numbering here, they would call this O-dichloral benzene. The O meaning ortho, and that means that you have both of those groups at carbon 1 and 2. The 1,3 positioning here also has a special name when you're dealing with specifically benzene as the main part. That is the meta arrangement, and that is sometimes just used as an M, and instead of 1,3 you would write M dichloral benzene. And the 1 and 4 positioning that we see over here, that is what is referred to as the para positioning, and sometimes just use a P, and that would be P dichloral benzene. So when we're dealing with benzene rings and we got a couple groups attached, sometimes ortho, meta, and para are used in place of numbering, but they do represent sort of the number location on the ring. So again, ortho represents the 1 and 2 positioning where you have groups. The meta is the 1 and 3 positioning on the benzene ring, and the para is a 1,4 opposites of each other basically on the benzene ring. Will get you that positioning. Ortho kind of next door to each other on the ring, and obviously meta 1 down from each other from on the ring. Any question on ortho, meta, or para, what they represent? And again, that is used specifically for only benzene as the main ring and 2 groups sort of attached to it. All right. So let's take a look at some of these names. When we do have toluene or phenol or aniline in there, we do sort of use that as the base of the name. So if we look at this part right here, actually, I'll just highlight it. If I highlight the ring here and my nitrogen containing group, that is the aniline part of the name. So that is where that comes from. And because that is kind of like the longest carbon chain, and that's an important functional group, that would make this group carbon number 1, which means if we go clockwise here, that's going to give us the smaller number there for our bromine, and that is how we get to the 3-bromo part of the name. So this would be 3-bromo aniline in this case. Question on that there. Now over here, we got a bunch of stuff happening, but maybe not so hidden in there. We do have one of those historical sort of benzene names, and we got a benzene ring with an OH group, and that is phenol. And again, that is where the base of the name comes from. We then have 2 groups hanging off of it, a chloral group and a bromol group in this case. And we will number, in this case, to give us a smaller number, counterclockwise, 1, 2, 3, and 4. The reason we don't go clockwise in this case is the first group would end up at carbon number 4, right? So 4 is obviously bigger than 2. So we do want to go counterclockwise in this case. And that gives us the location of each of those. 4 bromo. So even though it has the larger number, alphabetically it comes first because B before C. And 2 chlorophenol in this case. Any questions on how we get to that name there? Now, lastly, here we have some toluene in here as well. So once again, this is the toluene part highlighted right there. And that gives us actually 3 groups in this case. We got 1 bromine, 2 bromines, which gives us our dibromal part. We also have a chloral, which gives us our chloral part. And again, in terms of numbering, in this case, it really doesn't matter which way you go. Everybody's going to end up at the same numbering. And that's going to give us the bromines at carbons 2 and 6. And we do need to give both locations of it. And that's going to give us the 2,6 dibromal. And our chlorine will end up at carbon number 4 there. Once again here, ignoring the prefix. So B comes before C in terms of the alphabeticalness there of our groups. Any questions on how we get to all those names there? All right. Okay, so let's take a look. Obviously, we have a benzene ring, which should be the main part of it. That means that it will eliminate this guy, I imagine, because that says cyclohexane, which is not the same thing. That means that one of these 2 are okay. We do have a chlorine there, right? So which one should it be? It should be B. In this case, it is monosubstituted, which means you do not need to give the number because it's the only thing on that ring, and wherever that is located would be carbon number 1. So it should be chlorobenzene in this case. Any questions on that one there? Coming down here, we got a lot going on, and I do not see a toluene name in there, so we'll go regular naming on this. So we still have, obviously, as our main part here is benzene, which keeps all these guys here in the running. We have a methyl group here and a methyl group there, which means it's a dimethyl, which still keeps them all in the running here. At this point, we want to give some numbering, and we could start numbering perhaps up here, which would give us 1, 2, and 3. We could also go here as 1, 2, and 3. Obviously, if I went the other way, 1, 2, 3, 4, and 5, that seems like a lot bigger of a number there. So that would not be a good way to go. So it doesn't really matter in terms of which one you start with in this case. We do end up at carbon 1 and carbon 3 in this case, which means we should end up with that. And that would give us our 1,3 dimethylbenzene. This is also what arrangement? 1 and 3 is meta. So this could also be called meta dimethylbenzene without the numbers. So RM. So again, if you see like most likely they would probably just put M, and it'll be dimethyl benzene. By the way, if we went historical name on this, could also be, get rid of all my scribbling here, right? Could also be if we took this whole thing as toluene, right? And then that would be 1, 2, and 3. So that could also be 3-methyl toluene as well, would be a more historical sort of name. Any questions on benzenes? So again, those 3 that we saw there on that slide, the aniline, the toluene, and the phenol are very common ones that still come up, and people still kind of use those names. So you should be kind of familiar with those. Continue on here to chapter 12. We're going to talk about a bunch of organic type of groups. Some of which we sort of jumped ahead a little bit and talked about alcohols, but we're going to kind of officially go through the slides to say we officially did it, I suppose, but not much will change, I suppose, on those guys. So we're going to talk about alcohols, thiols, ethers, aldehydes, and ketones in this chapter. So these are a lot of carbon, oxygen sort of containing groups, and some with sulfur, which is our thiols here. So let's get into each of these. So alcohols, as we just kind of saw in terms of our functional groups. And again, you do need to know the functional groups of these different organic compounds. That is an OH group, which then makes it an alcohol. A thiol, as we'll talk about here in this chapter, has a functional group of a sulfur and a hydrogen here, like a sulfur containing group. Ethers have a functional group of carbon, oxygen, carbon. So that run of a carbon to an oxygen to a carbon. Single bonded, by the way. Aldehydes, as we saw with some of our reactions there, has a functional group of carbon, oxygen, double bond with a hydrogen. And ketones has a run of 3 in a row carbons, and always in the center of that 3 in a row carbons, you'll find the carbon oxygen double bond, which is sometimes referred to as the carbonyl carbon, or carbonyl group, which is that carbon oxygen double bond. So when we see that carbon oxygen double bond, it is, by the way, a polar bond, oxygen being more negative, carbon being more positive. This is sometimes referred to as the carbonyl group, and that's the carbonyl carbon, which has the carbon oxygen double bond basically attached to it. Again, in organic chemistry, a lot of times people will leave off the electrons there on the oxygen, but they are still there, just like in Lewis structures. So technically speaking, this oxygen still has those two pairs of non-bonding electrons on it. But sometimes for simplicity, so there's not so many dots all around in organic chemistry, sometimes those things are left off. But again, they are still there just to make everybody get that octet rule. So we're going to talk about each of these groups, obviously, in more detail as we go through this chapter, and we'll talk about what you need to know for these groups. Once again, here are our functional groups, our OH, our phenol, which again is our OH with our benzene that we just talked about. That is our carbon, oxygen, carbon run there for our ether. That is our sulfur containing group for our thiol. There's some of these other guys as we go through it. We'll talk about how to name them. So we'll get into our alcohols again here officially. We kind of talked about it obviously previously, but again, a reminder, alcohols will end in OL, just like alcohol name ends in OL. It has that functional group of OH. And again, that is what takes the priority in terms of naming, in terms of numbering. And again, you want to give that OH group whichever way gives it the smaller number in terms of the carbon location. There are some common names sometimes that are used for some simple alcohols. So for example, this guy here that we see on the bottom, this is a 1 carbon alcohol, and 1 carbon again is based off of methane, and we would drop the last part here, and now this would be known as methanol, OL. And in this case, because there's only 1 carbon, there's only 1 place where that OH group could be attached, so you do not need a number. So again, it's about 3 carbons with alcohols where you got to start giving the number of where the OH group is located. Same thing with ethanol. Ethanol looks something like this. Draw it out. And that is 2 carbons based off of ethane, and this would be ethanol. Now, you may be saying to yourself, but isn't there like 2 carbons? If I throw the OH group on the guy on the left there, won't it be something different? Will it be something different? It would not, because if I threw the OH on the left, then that would become carbon number 1, right? And if I throw the OH on the right, it's carbon number 1. It's the same molecule, just turned. So that's why we don't need the number or anything like that for that. But again, when we get up to propane, that's where we really start to need the numbering that happens. Now, sort of a abbreviated name or common name for alcohol, especially these couple, is to just name the group that's attached, so the CH3, and call it methyl and then alcohol. Our ethyl alcohol is the same thing as ethanol. Methyl alcohol is the same thing as methanol. So sometimes for those kind of guys where you don't really need numbering or anything like that, they'll kind of just name the group and then just put alcohol at the end as sort of the common way of naming it. We mostly will go with the IUPAC way of naming, which is, again, the more sort of official way of naming it. All right, so why don't we name this guy here? See what you come up with. Okay, so looking at this, we again want the longest carbon chain. In this case, it has an OH group, which tells us it's an alcohol, so it does obviously contain that. Straight across gives us 1, 2, 3, 4, 5, and 6, which I think is a winner. You could also get 6 if you started up here, 1, 2, 3, 4, 5, and 6. So you could go that way if you wanted to. Once again, as we talked about previously, if there is sort of more than one way you could go, it doesn't really matter in most cases which way you choose. It should give you the same answer at the end. Sometimes just going the straightest way there is a little bit easier maybe to see everything else that's attached. So clearly here we have an OH, which is really not necessarily a group, as is part of the functional group here. But in terms of group, we do have this guy, which is a methyl group, right? A 1 carbon group. So we got 6 carbons, which is based off of hexane, and we have the alcohol there, which makes it hexanol, OL. Do I need to give the location of the OH group? I do, because again, it's 3 or more carbons here. So you could probably see it just looking at it. I should probably number right to left here. That's going to give that OH group the smaller number. So that's going to be 3, 4, 5, and 6. So that's going to put a 2 in front of the hexanol. And once again, the 2 is the location of where the OH group is on that carbon chain. Now, as we've been talking about previously, now that we sort of locked in the numbering, we're stuck with it for our group that's there. So that means that our group is going to be at carbon number 5, and that's going to be a 5-methyl 2-hexanol. Any question on that name there? All right. So why don't you give the name for these guys? Why don't you also give the name for this guy? Why don't you also draw, let's do let's do 4-methyl 2-heptanol. Let's draw one. Let's do 2-bromol cyclopropanol. All right, so name the guys on the left, draw the ones on the right there. A, and we're looking again for the longest carbon chain. And I think if we go just straight across there, that's going to give us 5. Once again, we could have started up here, went down, and then to the right would also give us 5, I believe, as well. So either way will get us 5. Again, we do have, if you want to sort of add it there, part of that is the OH group, which makes it an alcohol. So 5 is going to be based off of pentane. And with the alcohol, they're going to be pentanol, OL, as our base of our name. We have, again, our methyl group hanging off over here. And we do want a number just like the previous one there. It does look like if we go right to left here, that's going to give our OH group the smaller number. And that means that this would be 2-pentanol for the location of the OH group. And because we locked the numbering in there, that moves our methyl to carbon number 4. And that would be 4-methyl 2-pentanol for A. Yeah. Any questions on that one there? No. Taking a look at B, we have actually in there a benzene ring, right? With an OH on it. So that is going to be our phenol, right? Which is that whole thing. So that's one of those historical names that again still used. So that's going to be phenol. Now, because that OH is really sort of part of the longest carbon chain and functional part, that definitely will be carbon 1 in our case. And you could probably see if you go counterclockwise in this case, that's going to give our bromine a 2 and then a 3. Obviously, if we went this way, we're going to get a much larger number for that bromine. So that would put it at 3, and that would be something like 3-bromol phenol in this case. Yeah. Any questions on those names there? That means that this guy up here is this phenol as well? It is not, because there's no double bonds, right? So that is basically cyclohexane with an OH group, right? Which means that is basically cyclohexanol, right? So again, no double bonds, not benzene. So that part right there is going to be our base of our name, which would be cyclohexanol, as it's basically based off of cyclohexane. This means that really where that OH group is going to be carbon number 1. And in this particular case, it doesn't really matter which way you go. I think if you go counterclockwise, that is 4. If you went clockwise, that is 4. So it doesn't really matter in this case. And that does happen. So that's going to put a 4-chloral cyclohexanol. A question on that one there. Yeah. So again, sometimes when people see that like 6-member ring and they learned about benzene, everything becomes benzene. Yeah, so it's got to have the double bonds or the circle in the middle to indicate that there's double bonds. Any questions on any of those names there? We're going to draw, and once again, always when we're drawing, we're going to go backwards here. And if we go backwards, I'm going to clear out some space to go backwards with, I think. Oh, let's clear this guy out. All right. So heptanol, OL tells us it's an alcohol, and heptane tells us it's 7 carbons. So we'll start back here. 1, 2, 3, 4, 5, 6, and 7. I think I got them. And once again, you just want to start with the carbons. OL tells us an alcohol. The 2 here tells us that OH group is at carbon number 2. And once again, since you are drawing, you could go left to right or right to left. I'm going to call this guy over here carbon number 1, which means for me, my carbon number 2 would be right about there. And that's where I'm going to put my OH group there. That will pretty much take care of this part. Since I went left to right here, that means I do need to keep that numbering for the methyl group. And that means for me, and if you did the same sort of numbering, your methyl group should end up over here at carbon number 4, right about there. And again, you could go up or down, really. It doesn't matter if you drew it up or down, either of those. At this point, there's nothing left of the name, so we're just going to fill it up with hydrogens to get the 4. So we need 3 here, need 2 there, need 2 there, need just 1 there, couple there, just 1 there, and 3 there. That obviously would be the condensed formula that I just drew right there. Yeah. Any questions on that? We were going to do our line. We would do the same thing. We would start with the 7. So 1, 2, 3, 4, 5, 6, and 7. Again, here, carbon 2 for me would be there. And carbon 4 would be right about there. And that would be it. I'm out of lines, I think, at that point. And it looks something like that if you drew a line structure. again, just a line with nothing added, is a methyl group. Yeah. Any questions on that drawing there? Coming here, we got a little cyclopropanol. So OL tells us it's an alcohol. Cyclo tells us it's one of those ring structures, and propane tells us it's 3 carbons. So that is our favorite one, which is a triangle, I suppose. Yes. And if I just leave it as a triangle, it's not an alcohol, so I do need to put a OH group on it. And it doesn't really matter where you put the OH group, because that guy should always be carbon number 1. I'm just going to put it up on top here. And that means that this would be carbon number 1. And that means carbon number 2, left or right, in this case, it doesn't really matter as well, would be where we would put our bromine, right? And again, if you put it to the left, it's okay as well, because that would also be the same guy just turned, basically. Any questions on drawing or naming alcohols here? All right. So a little bit more about some of these alcohols. Ethanol, which is ethyl alcohol. Again, that common name is the alcohol of alcohols there. We go through fermentation of grains and sugars and starches, and you get the alcohol there. It's produced through the reaction of ethene and water as well. Again, this is a hydration reaction, which will produce the alcohol by getting rid of the double bond, as we talked about earlier, and making it a single bond and putting that OH group on there to get us to our alcohol here. Here are some other alcohols. Some alcohols actually have multiple OH groups on it, and it has 3 OH groups, and that will have an effect on water or alcohol's ability to interact with things like water. So very small alcohols, as I think we might have talked about last time, are going to be soluble in water, and that is because the alcohol has this OH group, which is a polar group, just like we talked about with bonding, and that's more negative and that's more positive. So alcohols that are small can hydrogen bond with water through the opposite attraction there, negative of one to the hydrogen of the other, will be able to hydrogen bond. That makes small alcohols, 4-ish or less, fairly soluble in water, because of the ability to hydrogen bond. Is not really large either, those molecules, so they work okay with water to hydrogen bond. When you start building out the back part there of these alcohols to greater numbers of carbons, 7, 6, 7, 8, 9, 10, however many more, what ends up happening is, even though you have this small polar part on your alcohol, because you built out a ton of carbons with hydrogens, I'll just keep going off the screen here, and all those guys would have hydrogens. What happens is the non-polar part of that alcohol is now too big to allow that polar part to interact well with water. Water gets a little trouble trying to get in there. It also creates a much larger molecule, which doesn't fit well with all the smaller water molecules. So the solubility drops to almost nothing when you hit kind of like that 5, 6, 7, 8 carbons and stuff like that. But before that, things like ethanol, things like methanol, propanol, they are soluble in water because they're small. They have that OH group. They're able to hydrogen bond with water. So when we have something like what we see here, where there are multiple OH groups, it actually does increase its solubility with water, because everywhere there's an OH group, it gives it the ability to interact with water and to hydrogen bond with water, and it makes it a lot more soluble. This is also why earlier maybe we talked about sugar, which has a bunch of OH groups on it, and that's why sugar is soluble in water, because it has a bunch of OH groups. So everywhere there's those OH groups, it also allows it the ability to hydrogen bond and be soluble in water. In addition, with alcohols in that OH group, it can hydrogen bond with itself. So alcohols, when you have 2 alcohols, I won't say 2 different alcohols, but the same alcohol, 2 different molecules of the same alcohol. So if you have a little methanol, when it is there with another methanol, it also has the ability to hydrogen bond between the oxygen and the hydrogen, as I almost missed it there. And they're able to hydrogen bond with each other. And because hydrogen bonding is a really strong intermolecular force, that has a big effect on things like the boiling point of alcohols. So alcohols have really high boiling points because it is a very strong association between the alcohol in itself. So it takes a lot more energy to break that strong hydrogen bonding. And the result of that is it has a much higher boiling point. So alcohols, in terms of a lot of organic molecules, is almost the champion there in high boiling points and melting points as well, because of its ability to hydrogen bond. Again, you do not see that in alkanes, alkenes, alkynes. Those are all carbons and oxygen, carbons and not oxygens, carbons and hydrogens, which are all non-polar. So those guys are using super weak dispersion forces, which means they're not held together very tightly. And it doesn't take a lot for those guys to kind of go in the gas phase, as we might have talked about last time. Things like methane, like when you light your Bunsen burner, propane, butane, a lot of those guys are gases under normal conditions. And that's because they're using dispersion forces, which is really, really weak interactions. And it doesn't take a lot of convention for them to go into the gas phase. So they have very low boiling points compared to something like an alcohol, which can hydrogen bond with itself and be a very strong bond and takes a lot more energy to get it into the gas phase. So if something has in organic chemistry the ability to hydrogen bond with somebody else, it could also hydrogen bond with itself, and that makes it very high in terms of boiling points. And alcohols is pretty much the champion in terms of boiling points. There are a couple things that can defeat it in terms of high boiling points, and we're going to talk about it later on. But for now, alcohols is pretty much up there in terms of the highest boiling points and stuff like that, melting points that you would expect. Any questions on that there? This is ethylene glycol. It's antifreeze. So it's an alcohol. It's got a couple of OH groups there. Put that like in our cars, and it actually does two things in our cars. It makes it so that it doesn't overheat in very hot temperatures. It increases the boiling point actually of water in your car. Also decreases the freezing point, so you don't freeze if you live in a really cold area and get in your car and try to turn it on. Everything's all frozen. So antifreeze actually does both things. It increases the boiling point and lowers the freezing point. And that's the structure basically of it. It's also used in other things like paints and plastics as well. That's our BPA, again, with some of those polycarbonate bottles, but we can see our alcohol group here at the ends in each of these cases. So let's talk about another reaction that alcohols undergo. So far we've talked about several different reactions that alcohols undertake. We talk about making an alcohol by a hydration of an alkene. So adding water to our double bond will make the alcohol. We could actually reverse that process by dehydrating an alcohol. So when we dehydrate an alcohol, we're going to take away the water. So as we saw earlier, when we were looking up those reactions, a hydration reaction is when we're adding H and OH, which is our water. And just like we talked about, that's going to become a single bond. And that's going to allow our OH to end up on one and our H to end up on the other. I'll just circle it here as those things coming on. And that makes our alcohol. So hydration is putting the water on and making the alcohol. Dehydration is taking the water off and bringing it back to the alkene. So in a dehydration reaction, it's sort of the reverse of this reaction. And dehydration means that we're going to remove water. And the way that we put on water is, do both parts of water go to the same carbon or different carbons? They go to different carbons. So when we remove the water, we need to remove the water component from different carbons. So when we have an alcohol such as this guy here, and we heat it, which is sometimes abbreviated with a triangle on the arrow. So if you see that triangle, it means heat. This again is an acid catalyst to help this process out. we're going to take water off. So clearly one part of water is the OH, so that is this guy. The other part of water is a hydrogen that needs to come from the other carbon. So opposite carbon, we're going to take a hydrogen. That is going to get us our water that's going to come off. Now, once again, if you were to draw this, what should you draw? You should draw this guy exactly like that without the two hydrogens is essentially what you should draw. So you should draw over here exactly the way it looks without those two hydrogens that we took off. Now we know, I'm sorry, not hydrogen and OH that we took off, not the two hydrogens, but we took hydrogen and OH off there. Now, clearly, when we take off the water, we have to put something back in its place. So just like when we put the water on, we got to get rid of the double bond. When we take off the water, we got to basically put the double bond back on. So we're going to double bond between the two carbons where we remove the water. So this carbon right here is where we remove the water from, and that is where we're going to make our double bond. So when you do a dehydration of an alcohol, you're going to remove water as H and OH from opposite carbons. Then what you're going to do is double bond up those carbons where you remove the water from. Everything else in that molecule will be exactly the same. Nothing else changes. You just draw it exactly the same. Any questions on that reaction? Now, I'll do it here. If you remember when we put on our water, there was a difference, right, where the hydrogen could end up if we had differences in the hydrogens where the double bond was alcohol. And I wanted to basically dehydrate it, so I'm going to heat it up. So in this case, I know for sure I should take water out, which means for sure what things should come out? The OH. So for sure we got to get rid of that OH. Now when we look at it and we get rid of this OH here, the other part that we need to have in addition to the OH is the hydrogen. Now the hydrogen needs to come off of a carbon that is next to the OH group, right? The carbon that has the OH group. In this case, I actually have two carbons that have hydrogens, right? So I have some choices. If I take it off of this carbon, my double bond will end up right about there, right? So if I did take it off of that carbon on the left, I would have this structure, which I'm just going to copy exactly the same as what is there, except obviously taking off my water component in this case. And since I did remove my hydrogen between these two guys, I'm going to make my double bond there between those two guys, right? So that's one option. Call that option A, I suppose. Option B is I also got me some hydrogens there on the right-hand side that I could remove. So option B is if I take the hydrogen to the guy to the right. So I'll kind of take this guy, for example. Once again, if I'm going to draw it, I'm going to copy it exactly the same. So in this case, I would have a CH3. I would have a carbon. I would keep that hydrogen because that's not the one I'm removing. I'm going to get rid of the OH there. That's above this carbon right there. We're going to have a carbon there. I'm going to get rid of the hydrogen above this carbon and keep the other hydrogens. So here I remove the OH that was here and the H that was there, basically, right? Now that I removed the OH and the H, my double bond should end up between those two carbons that I removed them from. So I should end up with a double bond over here, I believe. Yes. Any questions first off on the two options? So clearly it's organic chemistry, so there must be a rule, right? So let's think about the rule here. The rule of putting on the water is the hydrogen should end up at the carbon that had the most hydrogens. When we take off the hydrogen, when there's an option like what we have in this situation, we actually take the hydrogen off the one with the least number. So kind of the opposite there. So the right one here would actually be A, right? So the structure here, A would be the right one. That would be really our major product. So we do take it off the one with the least number of hydrogens. So this guy has 2 hydrogens to begin with. This guy had 3 hydrogens to begin with. So we would want to take it off the guy there on the left and make our double bond between those 2 carbons. So it does happen when you do a dehydration of an alcohol that there could be a choice as to where you pull the hydrogen from. And if there is a choice and there is differences in the number of hydrogens on those carbons, you should choose the one that has the least. And again, that's opposite of how we put it on, which is the hydrogen goes to the one with the most. Yeah. Any questions on the difference there? Yeah. Okay. So those are some dehydration reactions. Hydrogen. So in this case, there is options, right, as to where we can remove our hydrogen. So we want to sort of analyze how many hydrogens we got going on those carbons. The guy to the right there has 1 hydrogen. The guy to the left there has 3. So the hydrogen should really come off of the guy on the right, right? So now that you sort of put some arrows there, now we know what we're going to take out of this structure. Remember that you pretty much have the answer right there in front of you, right? So I'm just going to copy exactly the way it looks. Obviously, I'm going to take out what has the arrows there, the water part of it. So again, nothing's going to change here. We're going to look exactly the same. We're going to take out the OH there, obviously, on that one. We're going to leave the BR there as well. We're going to keep this guy like he was. And now between the 2 carbons where we remove the water, we do need to insert our double bond back. And there we go. Question on that one there. So again, I can't emphasize enough that when people try to draw these things, they kind of freak out sometimes. And again, you want to remember that, you know, you kind of have almost the answer in the problem itself. So you don't want to overlook those sort of information that's given to you. And all these sort of reactions that we're talking about, pretty much only one small little part changes. And that's where you want to focus in on. And then pretty much just leave everything else alone. Just leave it exactly the way it is. Just change the part that needs to be changed. Any question on that there? So obviously, we talked about oxidation and reduction. So officially here, a reminder that the 2 definitions for oxidation and reduction that we see a lot in organic chemistry is the oxidation being the gaining of oxygen as you go from reactants to products. So somebody gains some oxygen as you go that way. And the second definition of oxidation is the loss of hydrogen, or H2. Reduction is basically the opposite of that. It is the loss of oxygen as you go from reactants to the product side, and it is the gaining of H2 as you go from reactants to products. So those are really the things that we look at, especially with organic molecules, because it's a lot harder or easier than looking for like charges and electrons and oxidation states, because organic compounds are pretty much nonmetals. So we have the kind of sharing of electrons that's happening. So we've gone over it a couple of times here, but just a reminder that in the case of the oxidation of our primary alcohol, we're going to remove H2. And again, it is always the hydrogen from the oxygen. It is always the hydrogen that is attached to the carbon in that OH group. And basically, you just put your double bond between the carbon and the oxygen, always in this case, and you will get your aldehyde. Now, one thing that we didn't talk about was sort of what can happen with our aldehyde here. And what can happen is, in addition to starting with our primary alcohol that goes through that oxidation reaction where we lose that 2 hydrogens and we make our aldehyde in this case, which again, this is the functional group here of the aldehyde. You could actually then oxidize the aldehyde one more time. So you could actually take it one more step past the aldehyde, and you could go through an oxidation. What's actually going to happen here is a lot more complicated than I'm going to explain, but what actually happens here is we're going to use the definition of oxidation of actually gaining oxygen. So the first step of this oxidation, where it goes from the alcohol to the aldehyde, is the loss of hydrogen. The second oxidation that will occur is actually the gaining of oxygen, is what's going to happen here. And to make it really simple, where that oxygen will end up is a blank screen. No, it will end up right there. It's going to end up right there. Everything's going to stay exactly the same. We're just going to kind of insert an oxygen right at that point where the hydrogen is. We're going to still keep the hydrogen. So I'm just going to draw it down here as I'm running out of screen there. Everything, once again, stays exactly the same. So I'm just going to copy what I got going on over here. I'm going to do an H and my carbons. I'm going to do my carbon-oxygen double bond. All stays the same. And here's where we're going to insert our oxygen. So we're going to put our oxygen at the back end here. I'll make it a different color so we could kind of see it. We're going to put our oxygen right there. But once again, we're still going to keep our hydrogen. So that is the result of an oxidation of an aldehyde, which is kind of two steps from our oxidation of our primary alcohol. By the way, this, as might not be a surprise, is another organic compound. This is our friend, the carboxylic acid. So carboxylic acid has the functional group of carbon-oxygen double bond OH action happening. That is the functional group of it. So if you take a primary alcohol and oxidize it once, you will end up with an aldehyde. If you then take that aldehyde and oxidize it again, you will end up with a carboxylic acid. Any questions on that? All right, so our secondary alcohol that we talked about, maybe somewhere, there it is. Our secondary alcohol, that's still our primary. How about our secondary alcohol? There it is. Our secondary alcohol, as we oxidize it, once again, taking the H from the OH and the H from the carbon that has the OH group, will give us our ketone here. And once again, our ketone is our 3-carbon run with the carbon-oxygen double bond in the middle. And for reference point, that is right about there, is our ketone group in this particular case. Now, what would happen if I wanted to oxidize this guy one more time? Well, sort of key to the oxidation step, if you remember, is perhaps the hydrogens being there, right? This guy does not have a hydrogen there on that carbon where the oxygen double bond is. You cannot oxidize this guy any further. You get no reaction because this guy is actually missing a hydrogen, which is sort of essential for the oxygen to come in, but so it will not occur in this case. And the reason it works in the case of our primary alcohol, when we get to the aldehyde, is this guy still has the hydrogen there. So it's still available to allow that oxidation reaction to occur. But when we make that ketone, there is no hydrogen there at the end. It is a carbon at that point, and we don't have that extra hydrogen that's necessary. This is really big for next week's lab, which is how you can tell the difference of whether you started with an aldehyde or a ketone. You could oxidize an aldehyde to a carboxylic acid. Ketone, no go. You do not get a carboxylic acid or anything happening there. You get no reaction when you try to oxidize it. So primary alcohol could go a couple of steps down the road through oxidation reactions, ending up with a carboxylic acid, which is another organic group. Our secondary alcohol could be oxidized once to a ketone, and then it's going to pretty much die out there in terms of oxidation reactions. And to finish up here, obviously, as we talked about previously, our tertiary alcohol, right, will not go through an oxidation because it is missing also that hydrogen that is necessary for that to happen, which is here. Once again, it does have this hydrogen, but this guy is missing that second hydrogen. for just the alcohol to go through an oxidation reaction. So as we summarized last time, and to finish here this time, a primary alcohol can be oxidized to an aldehyde, which then, as we just saw, can continue to be oxidized to a carboxylic acid. A secondary alcohol can be oxidized to a ketone, will not get oxidized any further. And a tertiary alcohol cannot go through oxidation because it's missing the hydrogen, so it just kind of sits there. So, any question on those reactions? Obviously, the reduction reaction in each of those cases, as I think we talked about earlier today, is the opposite, putting the hydrogen back on. For your ketone, if you put your hydrogen back on, it will go back this way. So if you add some hydrogen to the guy on the right, you'll get back obviously your alcohol. And the same thing with our primary. If you add some hydrogen to the guy on the right, it will go back to the alcohol, which is the reduction, basically the opposite of the oxidation reaction in each of those cases. Any questions on any of that? Yes. I laid it up there too soon. Thank you. When we go one more slide there, I think. Thank you. It's actually, which way am I going there? Just our primary. Wherever it went there. There it is. That's oxidation. Whoops. Here, let me just draw it. So if we have our aldehyde and we add some hydrogen to it, it's going to add right there, take away the double bond, and you will get back your alcohol that you started with there. That slide went somewhere. They all kind of look similar, but you will get there. You can. So if you had you add your hydrogen here, it will add there and there, just like a carbon-carbon double bond. Everything else will stay the same, and you'll get back your alcohol. And that's the reduction reaction, basically, of all those oxidation reactions that we talked about. There you go. So going backwards is adding the hydrogen back. Tertiary obviously can't be oxidized, so you can't go backwards in that case. Other questions on that?